This video is about bit manipulation, and this covers 4.3 from the CIE specification. Obviously it applies to some other exam boards as well, and it's part of the A-level course, so there's a set of videos for this course, so please check those out. We may want to manipulate bits in a binary number. There's a lot of uses for this. We can do mathematical operations efficiently with them. We can control systems. We can have a set of flags in a very small amount of storage and be able to set and clear those flags. We can manipulate colors because obviously colors, like everything else on a computer, is just represented by binary numbers. So we can change colors easily by changing the bits in the color information. It's used for encryption and also error detection. So lots of times we might want to just be able to effectively play around with the bits in a binary number and come up with something different, something new. And obviously the meaning of that depends on the situation. So we're going to look at two kinds of bit manipulation. The first one is called logical bitwise operations, and the other one is shifts. So let's look at the bitwise operations first. There are three that we're going to be using for this course. They're AND, OR, and XOR. So in an AND, obviously you AND pairs of bits, so you need two inputs for this. And OR, you OR them together, and XOR, you do the exclusive OR of the pairs of bits. So what does that look like? Here's an example where we've taken two binary numbers, so there are two inputs, and we're going to do an AND operation, but a bitwise AND operation. That means that we take every single bit in turn and them together. So I usually start over here on the right, and then we take these two numbers. These are our input numbers. 0 and 1 gives 0, because they're not both true. 1 and 1 is true, 0 and 0 not true, and so on. So we do that for every single bit through the number, however long it is. And then this is our result. So the bottom line here is our answer. That's the logical AND operation carried out on these two numbers. We can use this kind of bit manipulation to monitor and control devices. Things like I/O ports and sensors are often connected to registers, not the kind of registers inside the CPU, but they're in the device or the hardware interface for a device. And all they are really is a set of bits that represent something for that device. So it could be the state of a pin, a flag, or something like that. And the CPU will be able to read and write to those registers, manipulating the bits in the way that we're looking at right now. So for example, we might have a control register in a device where each bit indicates something like printer's ready, or it's out of paper, tone has run out, something like that. So every bit in the bit string in that binary number will have a different meaning. So each bit has a different independent meaning from the other ones. So we don't treat it as a whole number, as the whole thing. We're actually looking at the individual bits within the number to mean things. So to monitor the device, we can look at those bits in the register and test them to see whether they're a 0 or 1. So we're only interested in testing a particular bit at one time because we want to know one thing about that device. We can control the device by setting or clearing a bit in there. So for example, we might want to say start the motor, and one of those bits in that binary number is going to be controlling that. So we need to be able to set that and only that bit. Now to do this sort of thing, we can use bit mask, and a bit mask is just another binary number. It's a sequence of zeros and ones, but the specific sequence really matters. So to test a bit, any bit, let's say we want to test bit n, we're going to use the AND bitwise logical operator with a register where with a mask where it has a 1 only in position N and 0 everywhere else. So for example, if our register contained that binary number, remember this is not a CPU register, this is just in a hardware device or something, then we can use the mask they're given there where it has a 1 only in that position N. That's the bit position 3, 0, 1, 2, 3, that contains the 1. And then we use the bitwise operation AND with our register and our mask. And it will give us a non-zero result where when that bit is actually set to 1. So we can test that bit in that position with that mask and the AND operation. Because we've put 0 everywhere else, none of the other ones is going to give us any information because AND needs both of them to be true, both of them to be 1 for it to do anything. So that's isolating the one particular bit that we're interested in testing. In a similar way, we can set or clear bits. So to set a bit N, then we use an OR operation with a mask that has a 1 only in that position and 0 everywhere else. So in order to set it, we want to leave everything else alone. So we put 0 everywhere else, so we're not going to have any effect on anything else. If it was 1, it will stay 1. If it was 0, it will stay 0. Because 1 or 0 is just 1, and 0 or 0 is just 0, so it still stays the same. But where we put the 1, then if it's a 0 currently, and we OR it with a 1 that we put in the mask, then it will force it to become 1 now. If it was 1 before, it will stay as 1. So it's not changing it in that case. But that allows us to set one specific bit anywhere in that register. To clear a bit, we can use the AND operation with a mask that has 0 in that position and 1 everywhere else. So where there's a 1 everywhere else, whatever's there already will stay the same. So if it was already 1, 1 and 1 is still 1, so we stay there. If it was 0 before, and 0 and 1 is still 0, so there's no change. It's only where that bit that we want to clear is already 1, and we set the mask to have a 0 there, we end up with getting 1 and 0, which means it resets it back to 0. We can also toggle a bit, so swap it from one state to the other. So we can use XOR for that. And we put a 1 only in that position and 0 everywhere else. We can use this sort of thing for controlling lots of different systems. One of them might be a stage lighting system where we have many lights shining on the stage, and we want to control them in certain ways. So a whole set may need to come on or go off, or may to alternate what's already on to off and so on. And we can do that very precisely with the individual lights or multiple groups of light at a time by using the right kind of masks. So now we look at binary shifts, and there are different kinds of shifts: logical, arithmetic, and cyclic. All the shift is moving bits in the binary number to the left or the right. All shifts do that. The difference is what they do with filling the gaps. Okay, so in a logical shift, then we fill the gaps that appear at either end with a 0. So if we're shifting left, everything moves left, and a 0 comes in from the right to join in. Okay, if we're shifting to the right, then a 0 comes in from the left to make up for what's missing, so to fill that gap. So that's logical shifts. In our arithmetic shift, it's slightly different. We'll look at that a little bit more in a moment. And then cycling shifts, you don't want to lose any data. So instead of dropping it off one end, you bring it round and put it on the other end. So here's a logical shift of a binary number. We're moving it one place. So you can shift any number of places. It may be 1, 2, 3, or so on. And then a logical left shift is just moving everything left by one place in this case. And you can see there on the right hand end, we've had to introduce a 0 from nowhere. So that's just been pulled in to fill that gap that would have been left otherwise. Now, it is possible, obviously, for things to fall off the other end. If we shift it too far to the left, then this will break down because something will fall off the end, and that's an overflow. Okay, so actually the number's getting bigger as we shift to the left, and maybe you already know, but overflow is when the number becomes too large to store in the number of bits available, so in the fixed number of bits available. So you can see that the effect of shifting to the left is doubling it. And that makes sense because every bit that was there before, every one that was there before, is now in the next column along, which is worth twice as much because it's binary. Similarly, for the logical shift right at the bottom hand there, we're going to move everything to the right and fill in with a 0 on the left to make sure there's no gap there. So it has to be a 0 or 1, but in this case we're always going to be filling this with a 0. And you can see the effect there is to halve the number because we've done a shift of one place. It will be halved again if we shift it another place to the right. And the same sort of thing can happen is some bits could fall off the end and disappear, in which case the number is not accurate anymore. We haven't preserved all the information in the number, so this would cause a loss of precision. Now the arithmetic shift is slightly different when we're moving to the right. So if you've got a signed 2's complement number, which is our normal way of representing negative numbers, we will have a little bit of a difference. So first of all, a positive number on the left there will be just the same. We pull in a 0 and fill that gap on the left that would be there, and we end up with the correct result. So we've halved the number and there's no problem. If we're left shifting a positive number, again, no problem. We'll just move it the other way and fill in with a 0 on the right. So the arithmetic shift is just the same as a logical shift for a positive number like that. Where it gets different is when we're dealing with the negative number. So on the right there, we've got a 2's complement representation of -22. And you can see that the first bit is a 1, and that's effectively the sign bit. So when we shift to the right here, we can't just pull in a 0 on that end. So that would change the sign, that would make it a positive number, and we can't do that. So we pull in a 1 instead, and that preserves the fact that it's negative, and it's still half the number. If we're going to try and go in the other way, it behaves just like a logical left shift. And then we've got cyclic shift. So in this case, if we're shifting to the left one place, you can see the one that's in the bit on the far left, instead of dropping off and disappearing, it will be wrapped around and come back in on the right hand side. So again, there are no gaps, but what we've used to fill that gap is the one that was on the end, or the bit that was on the end, on the left hand end, and it's come back in the right. And obviously for a right shift it's the other way around, so it drops off the right hand end but comes back in on the left hand end of the number, and that's a cyclic shift. So just to recap, we've got these three types of shifts: a logical, arithmetic, and cyclic. We can left or right shift. A left logical shift, we pull in a 0. A right logical shift, we pull in a 0 on the other end. And this is used for unsigned numbers and just a general bit pattern if we wanted to do something number like that. Arithmetic, so left shift, that's just the same as logical. Right shift, we need to preserve that sign bit, so we copy the sign bit into the gap, and we use this for signed integers, assigned to complement integers. And then cyclic, we left shift, we take the bit that fell off the right, and right shift, we take the bit that fell off the left. No data is lost, and this can be used for things like hashing and cryptography. These are the assembly language instructions for CIE that do these kind of operations. So you've got the bitwise operations and or XOR, and you've got the shifts, the logical shift left and a logical shift right. They don't have any others, so they don't have the cyclic and they don't have the arithmetic shifts, so they wouldn't come up in actual example programs, but you might still need to be able to talk about how they work. And for each of those, there are different syntax formats meaning different things. So again, the AND means in the first AND there is bitwise AND with contents of the accumulator and whatever the operand contains. So that's an immediate mode where you're actually given the operand value directly in the instruction, and it's either hash capital B or ampersand. Hash means it's denary, capital B means it's in binary, and ampersand means it's in hex. So of course that's just for the human reading it as we write it in the way we want. So if I was denary number 5, I'll just put hash 5. It will actually convert that to binary, obviously, get 5 as a binary, and then do the bitwise operation and with whatever the binary contents of the accumulator are. Then the other syntax for it is AND with an address, and that could be a symbolic address. So it'll take the contents of that address and the content with the accumulator content. And the same for OR. You can have the immediate mode or the direct mode, and XOR. And the logical shifts, so in this case you're just given a number of places that you want to shift, and that's given as a denary number. So how many you want to shift left, 1, 2, 3, and so on, and how many you want to shift right, 1, 2, 3, and so on. So that's part 4.3, the CIE spec. And the next one is going to be moving on to operating systems.